All right, hi, welcome back to Statics 1. We've been talking about moments. We talked about evaluating moments in coplanar systems where everything's on the same plane. We talked about 3D system where you have forces and acting in the general case, not necessarily on a coplanar system. And I want to show you kind of a shortcut for evaluation of moments called the principle of moments. Let's see if this marker works. Principle, yes. Principle of moments. And I'll just, actually before I do that, why don't I just show you kind of the two ways we've been doing these. And if you have our, again, I'll draw my wrench here. And here's on my nut. So this is my point O, where I'm evaluating my moment. And we're applying a force here. And we know there's a couple ways of doing this. We could define a position vector. Let me do that in red. We could define a position vector like that, which we'll call R. If we know the Cartesian coordinates, and this is my force, and the angle between these is theta, or you can show it here, I guess. Then the moment equals R cross F, right? So we can do it that way. We can also do it, we know it's all just the perpendicular distance, so we can just say the moment magnitude anyways equals R times sine theta, which will give you that distance, R times F times sine theta. Okay, so those are kind of like the two methods we have so far, using vectors, using scalars. I'm going to show you a third way, which is called the principle of moments. I wrote it out here, principle of moments. The principle says that the moment, I'll write it out, okay? I'm going to write it out, which is that the moment resulting from a vector equals the moment resulting from a vector. In other words, you apply a vector like this one, the moment at that location equals the sum of the moments from vector components. Okay, so you can, the moment resulting from a vector equals the sum, right? That's the summation sign of the moments that would result from that vector's components. I'll put it that here. Let's put that in. So when we talk about vector components, we're talking about the vector components of this vector here. So let's see what we mean by that. And we took kind of, I think first day we started talking about vectors and their components. And all that means is if we have a vector f of r equal to f1 plus f2. It doesn't have to be force vector. It could be position vectors. This is the vector, and these are its components. It means you can add up one and the other. In the general case, we have something like a vector. This might be my f of r. And then we can have my f1 and f2 pointing off in different directions. But they have to sum to that f of r value. So here I'm going to use the parallelogram rule, and we'll prove that. I'll do it in another color so it shows up. Remember our parallelogram rule. So you can see that f1 plus f2 is going to be equal to f of r. Now that's useful, but when we actually apply the principle of moments, for the most part, we're not going to use this general components at some arbitrary like angles, but we're going to use what we call the rectangular components. And the reason is because they're easy to find and also easy, for the most case, you're going to find it very easy to evaluate the moments of a system like that. And I'll show you how it's done. So these are the rectangular components. So this is my FR value, and if we were in an XY plane, which you might think we are, and this is theta, then Fx equals FR times cos theta, because this is my hypotenuse. FR is my hypotenuse. I multiply it by the cos theta, which is adjacent over hypotenuse, and we get the adjacent value, Fx. And Fy, by the same reasoning, equals Fy equals FR times sine theta. This you need to really know. And really, I think I had mentioned this at the beginning of the term when we talked about when I reviewed basic trigonometry. You got to know these like so you can do them very fast, because you're going to be doing them like all the time. The more you do it, the easier it will get. I guarantee it. If it's hard in the beginning, don't worry, it'll get easier as you go along. Okay, so I'm going to erase the board, and then we'll come back, and I'll show you how to use principal moments. Next, I want to talk about the principal moments, how we actually apply principal moments. And I'm going to show you an example, basically, that I ripped off from the textbook. And let's see what it looks like. So you have a wall. If I draw, you see something like that, think wall. And we've attached to it kind of a triangular shaped thing. It has a height of 0.2 meters. This height is 0.2 meters, and it has a length in this direction of 0.4 meters. And I'm going to define my point O. We want to find out, actually I have to put a force on here, which is 400 newtons. 400 newtons, and it's basically 30 degrees from the purely vertical system. We want to evaluate the moment at this point O. Okay, so what do you think it is, and how can we do it? So we know we could define a position vector here, right, in Cartesian coordinates, write our F in Cartesian coordinates and go R cross F and get it. We could also do some trigonometry and figure out our perpendicular distance. We can do that, but you might find it easier to use what we talked about last time, our principle of moments. So what we need to do is we need to find the component vectors, find the moments resulting from each of the component vectors, add them together, and that'll give us the moment of that is caused by this 400 Newton force off in this direction. All right, so now I'm going to show you how to apply principal moments for the evaluation of a moment at that location resulting from this force. To do that, we need to figure out what is the moment from each of the rectangular components of that 400 newtons. So I have one of them over here, that's my f of x. I have one pointing downward, in other words, negative direction. That's going to be my f of y value. So let's start with f of y. Or let's start with f of x, since we usually do that. F of x, right? That f of x is essentially the same as that there, right? Because we know f of y plus f of x by triangle rule equals that 400 newtons vector. So this is my f of x value, and it's opposite the 30 degrees. So opposite over hypotenuse, sine, right, times 400 newtons, which is my hypotenuse, will give me the result of my f of x. So it's equal to 400 newtons times sine 30 degrees equals, and it's in the positive x direction. Positive, so that's good. So that's equal to 200 newtons in the positive direction. Okay, now f of y, and this one's we already know it's in negative direction, so I'm going to put a negative value here. And what is it going to be equal to? In this case, if you think of this triangle here, we have our 30 degrees, we have a length side adjacent to that 30, and we have a hypotenuse. So we're going to multiply the hypotenuse, 400 newtons, times adjacent over hypotenuse, which would be cosine of 30. Cos 30 degrees. And that's going to be equal to 0.86, and the result is 346.41. And notice how I keep like extra significant digits. The final result we're going to round off, but don't round off your sort of kind of in between results. I kept a few extra. We could. There's more digits beyond that we could keep. All right, so that is f of y. So I'm going to put right in here. So we have 200 newtons here, and we have negative 346.41 newtons here. And now we're going to basically figure out our moment about this point. Let's do the 200 newtons first. So we have 200 newtons off in this direction. The line of action is here. We draw a little perpendicular, little square here to tell us the perpendicular distance. So that's 0.2. That is the perpendicular distance. That's essentially the moment arm of our force going. The force goes in that direction. We basically lock down that point, and we're going counterclockwise, right? Because it's pulling it in that direction, counterclockwise. So that is a positive moment about our point O. So I'm going to write that down. So I'm going to write moment O equals, what are we talking? Oh, 200 newtons times this distance here, 0.2 meters. Okay, that's the result of the f of x. Now we're going to do the result of the f of y. In this case, we can do the same thing. We can draw the line of action. I'll do it in blue. What's left of my blue? There we are, blue. That's our line of action of our force. Our perpendicular distance essentially here, measured from that point here, and it's going to be 0.4 meters. And in this case, what is the direction caused by that downward force? It's going to be clockwise. So we need to make it negative. So it's going to be minus 346.41 newtons times 0.4 meters. And we can write out the result is negative 98.6 Newton meters. Okay, so that shows you an application of the principle of moments, and that's an application of the principle of moments. I think you'll find it a lot easier than applying R cross F or doing some other complicated geometry, trigonometry. And we're going to use this all the time when we get to like looking at structures, when we're talking about simplifying systems, which is kind of the next step that we're moving to in our next lecture. Send me an email if you have any questions, and otherwise I'll see you in class.